Welcome back. We're gonna continue from last time. Let's first recall the definition. So we started with the method of entropy, which is a notion coming from information theory. So let's recall. So the setup is that let's recall. The setup is that we have a random. We consider a random variable, discrete random variable. Over some finite set A. So X takes values in A. And the entropy, which we denote by h of x, assigns this discrete random variable a non-negative real value, which measures the amount of information that this random variable x carries. And there are two ways to define this entropy. The explicit way of defining it, we mentioned it last time, h of x equals to the sum over all instances of A, that the probability that x equals to little x times the log of reciprocal of this value. But I would recommend, as also I first saw this recommendation in Tim Gower's lecture notes, where we try to use the axioms, the abstract set of axioms. It has the advantage of saving us doing some calculations using this explicit formula. We can then just derive all sort of properties most of the time using abstract axioms. So the axioms, let's recall them. This is the Shannon Pynchon axioms. There are 6 of them. Some of them are not so important, so I'll skip some of them. Let me mention okay, I will mention all of them, but I will emphasize the important ones. The first one is important. It's called invariance. Essentially, it says that this entropy is determined only by the distribution of X. So what it means is that if you have two random variable having the same distribution, then their entropy will be the same. The amount of information that two random variables with the same distribution carry will be the same, which is intuitive. The second one, and the second one is called maximality, a very important one. So maximality says, well, we have X defined over A with, it could have all sort of distribution, but it will get different entropy. But the one with the maximal entropy, with the maximal amount of information or randomness or surprise we will get, is the one that's defined uniformly over the set A. So the entropy is maximized by uniform distribution. which is also which also makes sense if you think of a coin flip. If you flip a coin, it could have up and tail or head. Then if it's equal probability, that's the most difficult case to predict the outcome. Everything is equally likely. But if it's heavily weighted on the tail, if we know it happens with 99% probability is tail and 1% is head, then we know more certain what the outcome will be. The entropy, the amount of surprise will be less. The third one, extensibility. This is just some technical one. Most of the time we will not use it, but it just says that we can extend something just for technicality. You can go back and check the definition. The next one is important, additivity. Additivity says, well, if we have this guy, and let's recall what this guy is. So if I write this, probability that x takes value x as p little x, and then I can, this is basically, it's the same definition. You have x in A, y in B, then this will be pxy log 1 over pxy, where pxy means the probability that x takes value x, y takes value y. So this is the joint information that x and y together give us. This joint information will be the same as the information we get from x, and then the information we get from y on top of x. This is the conditional entropy. And let's also recall the conditional entropy definition is this is the the expectation over all possible values of outcome of x, the entropy of y, given that x takes this value little x. If you want to write it out, it's the x in x, px, h of y, x equals to little x. Okay. Once again, this is information we get from x. And then after knowing x, this is the additional information we get from y. Together, this is the joint amount of information. Additivity, important one. The rest two, just for technical reason, continuity, it says that the entropy depends continuously on the atom probability of x. And the last one, normalization, so that using this set of axioms, and then we have the right normalization, we can recover, you will uniquely determine that this choice of entropy is the unique one, satisfying this set of 6 axioms. And let's recall the basic property. We've seen also a quick application of this in the last lecture, which is the estimating the volume of Hamming balls using the binary entropy function. The basic properties, we started proving some basic properties last time, and we're going to continue doing that this time. The first basic property is the independence. The independence says that if two random variables, they are independent of each other, they have nothing to do with each other, then the set of information we get from them, they are also disjoint. So x, y are independent random variables. Then if the set of information they give us are disjoint, what is this conditional entropy? This is the information we get from y after knowing x, right? Let me remind you. This is information we get from y after knowing x, or the additional information we know from y on top of x. Well, since x and y has nothing to do with each other, knowing x does not give us anything about y. So this is still the same as if we don't know x. Another thing is their joint information is the same as each individual one, since they are independent, as I said. The amount of information they offer are disjoint. Independence, a very important property. Second one, the monotonicity. So I hope that this course, even though it's streamed online, I hope that it will be interactive. If you have any questions, you can type in the chat, or just you can turn on your mic and ask questions. Okay. So where was I? The monotonicity. Monotonicity basically says if you have two random variable uniformly distributed over, you have a random variables, x uniformly distributed over set A, y uniformly distributed over set B. The one that's distributed over a larger set will have larger entropy. So if A is at most the size of B, then the entropy of X is at most the entropy of Y. And furthermore, equality holds if and only if A and B has the same cardinality. Yeah, equality. Non-negativity. This is almost a trivial one from the explicit definition, but from the axioms, we can also derive this. It says that for every random variable x, the amount of information it carries is non-negative. Well, after knowing something, it cannot erase some memory from us, right? So the information can never be negative. All right. Now we're going to continue proving more properties. The first one is that, well, we know that it's not negative. We also know that when it's deterministic, I think we proved that I think we proved last time that when the random variable takes only one value, then did we prove this? If random variable takes only one value, then entropy is 0. Now, the next one is if the random variable is not a certainty, if it doesn't take only one value, it takes at least two value, then it must be strictly positive. For any non-trivial random variable, we get some information out of it. So this is the next lemma. So it takes at least two different values with positive probabilities. Then we get positive amount of information from it, which it also makes sense, intuitive sense. Let's see the proof. Well, from the set of axioms, the proof takes a few steps. So let's say x takes value on A. And let's define the maximum atom probability. Let C to be the maximum atom probability, meaning the maximum probability of a value that X can take over A. What do we know about this maximum atom probability? It's strictly less than 1 because of this hypothesis. X must have positive probability over 2 different values. So the maximum one cannot be 1. Now, since it's strictly less than 1, let's fix a small epsilon positive. No matter what epsilon we fix, since C is smaller than 1, we can take sufficiently large N. There exists large N such that C to the N going to be smaller than this epsilon that we took. Now we're sort of doing some sort of tensor power trick thing. We're going to consider IID copy, independent, identically distributed copies of the random variable X. So consider IID. So I'll use this shorthand notation. IID means independent, identically distributed copies, let's say X1, X2 to Xn. Each one of them has the same distribution as X, but they are independent mutually. So if you consider this random vector X1 to Xn is defined now over A cross A cross A, n copies. Let's call it A to the n. What's the maximum atom probability here? Since they are independent, each one has the atom probability C. So the atom probability for the whole random vector is C to the n, the maximum. So by definition, the maximum atom probability of this random vector x1 to the dot to xn is at most equals to C to the n by independence, which is less than epsilon by our choice of n. Okay. So we have this is our space. This is our space A to the n. Maybe I'll just draw it. This is our space A to the n, which is the space where this random vector lies in, taking values at. And each atom probability is less than epsilon. Then we can cut it into pieces of A0 and A1. We can define two events, cutting the whole ground set into two pieces, such that the probability measure of each piece is around 1/2. This implies that we can partition the whole space into two sets, A1 and A0, such that the probability that AI occurs is 1/2 plus minus epsilon. This means at least 1/2 minus epsilon and at most 1/2 plus epsilon. Is this clear? So what I just wrote down is that each little guy, so AN here inside, how many elements here? Each one of these dots is like A1 to the dot to AN, right? Each AI is in A. This guy, each one of these guys is events, which happens with probability at most C to the n. Now we group them up. Each one is at most C to the n, which is at most epsilon. You group them up into two groups. Each little guy has a measure less than epsilon. We can then cut them into two parts where it's roughly 1/2 up to epsilon. If they are more than epsilon apart, you move one guy to the other side to balance things out. Now we're going to define a random variable y such that y equals to I if and only if our random vector lies on the corresponding parts. Okay, I equal to 0 or 1. If and only if x1 to xn lies in AI for I equal to 0 or 1. Okay. Now recall by normalization, if this epsilon is not there, what's this random variable? If it's not there, this is the standard binomial Bernoulli random variable with one child, right? It's a coin flip, fair coin flip. So y is a uniform random variable distributed over a set of size 2. By normalization, the entropy of it will be 1 if this epsilon is not there. But since epsilon is there, it's going to be slightly off by 1. But remember, there's an axiom called continuity. So it depends continuously on the atom probability. Now, that means with this plus minus epsilon 1, we're not going to be too far away from 1, the entropy. So by taking epsilon sufficiently small, entropy of y is still going to be very close to 1. In particular, entropy of y is going to be positive. So by continuity, and normalization, the entropy of y is going to be positive. Now, we are almost done. Let's recall our goal. Our goal is to prove that entropy of x is positive. So we know entropy of y is positive now. But the last thing we have to notice to finish the proof is that y is determined by okay. I forgot proving something, but let me use this as black box for now. So y is determined by x1 to the dot xn. Okay. Simply because, right? We use x1 to xn to partition the ground set into 2 parts with almost equal measure. Then we define y. In terms of this random vector. So if you know how x1 to xn, the outcome, we know explicitly how y looks like. Y is deterministically defined by, completely determined by this random vector x1 to xn. So this is the property that I forgot to prove for you. Let's use it as black box now. If we have one random variable that is determined by another, then the entropy of this guy is at most the entropy of this guy. Then let's call this property dependence property. The entropy of y is at most the entropy of x1 xn. So this I need to prove it for you just right after this. Now let's look at the right-hand side. The right-hand side by independence, x1 to xn are IID copy of x. By independence, one of the previous lemma we proved that is the same as n times the entropy of x. And the left-hand side, recall, we proved already that y has positive entropy. We are done. divide both sides by n, h of x is positive. All right. So let's prove this dependence property, which I forgot. Okay. Any question about this proof? Okay. Dependence says we have random variables, x and y, as I wrote down above. Let's x and y. Now, think of x as this guy. If y is determined by x for some function f, then the entropy of y is at most the entropy of x with equality if f is bijective. So what this roughly means, let me write down, is that if the meaning is if y is determined by x, two random variable, one is determined by the other, then y does not carry more information than x. Does not carry more information than x. Let's see the proof. So if we prove this guy, we have everything we need here in the previous proof. Well, let's first look at this equality case. When f is a bijection, two are the same. This is just invariance principle that these two random variable basically has the same distribution. So their entropy are the same. So the equality case is just invariance principle. For the inequality, that's what we have to prove. Again, by invariance, let's recall. We can find the bijection between the joint random variable x, y to x, a bijection. So h of x, y is the same of h of x, if you recall the invariance axiom. Okay, this is the axiom we know from the hypothesis. On the other hand, what is this guy on the left? This by additivity says the joint information equals to the information we get from y plus the information we get from x on top of y. Okay? Now we are done because by non-negativity, this is at least zero by non-negativity that we proved. The entropy of any random variable, in particular this conditional one also, is non-negative. So this is at least this guy. Okay. The next property, a very important one, but the proof will be very simple. I will leave it for you. It's called chain rule. a very, very important one. If this is the first time you've seen entropy, it does seem like there's lots of properties I've introduced so far. Don't worry. Let's just try to understand one by one for now. And later, when we finish all this theory building, I'm going to summarize all the important ones that we're going to use throughout the proof. So don't get overwhelmed. So the chain rule says, if we have random variables, x1, x2, dot, 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 to xn, then the joint entropy of this vector equals to, okay, let me read it out using the informal meaning. The total information we get from x1 to xn equals to the information we get first from the first person, right? So we have m people here. The first guy, second guy to nth guy. The gossips, we will hear from them, the information we will get from them. First, we hear the story from the first guy, right? The information from the first guy. And then after hearing the first guy, we're going to hear the story from the second guy, right? And after hearing the second guy, we're going to conditional x1, x2, and hear the story from the third guy. That's the information. All the way till the end. What's the end? The end is the entropy of xn given x1 to xn minus 1. Given x1 to xn minus 1, we look at the entropy of xn. Now, the proof of this, I will just remark, additivity axiom additivity, spell it wrong, additivity gives the n equal to 2 case, right? And the rest you just use induction. And then induction. This is not even an exercise. Try to prove it. Make it rigorous here. A very important property. Now we're going to prove 2 more properties or lemmas, even equally important. One of them we've seen it already when we try to do this quick application on estimating the volume of the Hamming ball. That's the subadditivity property. That's the first one. But before that, we need to do something, prove one more property that's also intuitive. That's also intuitive, which is called dropping conditioning. So let me first say this. Now, those are the basic properties up to chain rule that we've established. Next, we're going to prove some lemmas about subadditivity. Subadditivity and Shira's lemma. Dropping conditioning. So the dropping conditioning is simple to state. It says that we have random variables. So we have random variables x, y, z. For any random variables x, y, z, then we have the conditional entropy of y given x is at most the entropy of y. And similarly, conditional entropy of z given y and x is at most the conditional entropy of y. I will only prove the first guy. The second one is almost the same. You just think of these as one, as the y here, right? Think of these as the y here. And you have additional, you drop this conditional, conditioning x. First of all, let's convince ourselves that this is something, this is not something insane we try to prove. On the right-hand side, that's the information we get from y. On the left-hand side is the additional information we get from y after knowing x. So if already x told you something, then you might already get some information. So what you get from x afterwards is no more than you didn't hear anything from x and you just hear the story from y. And by independence property we proved before, the equality holds if x and y are independent, right? So now we're saying we don't put any restriction on x and y. If we drop the conditioning, it's only going to decrease the entropy. So let's prove this. Consider, okay, so how do we prove this? Well, let's first, so this is the thing we want to prove. Let's see what we need. Let's write down left-hand side and right-hand side using the axioms that we know. When we have conditional entropy involved, the axiom, the corresponding axiom is the additivity axiom. So additivity axiom implies that the left-hand side conditional entropy equals to the joint entropy minus the entropy of x, right? The information we get from y on top of x is the joint information minus the information we've already obtained from x. And also, the right-hand side, hy, similarly, by additivity, is the joint information from x, y, minus the conditional entropy of additional entropy information we get from x on top of y. Both of these two are additivity. We want to prove this guy less than this guy. This is the same. So we need to prove this guy is larger than, is less than this guy, right? We need to prove this. Okay. So we need to show that this seems the same thing. We're going to drop in conditioning in different direction. But okay. So we need to show it seems like the same thing. But it's going to be slightly different. So let's try to, so now our goal is to prove this guy. Okay, if we have this guy, we have what we need. Let's try to prove, when we don't know how to prove something, let's assume something more to prove some special cases. And here, let's assume x is uniformly distributed. We want to prove this guy is larger, right? Well, look, here is a conditional one. And uniform distribution has the largest entropy. That seems like a good direction to go. So let's assume, consider the special case when x is uniformly distributed. In this case, for any choice of b from which the y takes a value, So if you condition on y takes value b, it's at most, this is a random variable itself, right? Now we fix the outcome of y. This is a random variable, conditional random variable, x. It's at most h of x. Why? Because x is uniformly distributed. Both are random variable, but this guy is uniformly distributed by maximality. Uniformly distributed one has the maximum entropy. And since this inequality is true for all choices of B, for all outcome of Y, then we can drop this outcome, and this implies that this guy is at most h of x. So we prove this case in the special case that when x is uniformly distributed. Now we have to prove the general case. For the general case, well, first of all, we may assume x takes rational atom probability, the usual trick, because of continuity. For the general case, by continuity, we may assume that x takes rational atom probability. So what it means is that the probability that x takes some value a equals to, let's say, m sub a, where m sub a is a natural number. Remember this, right? And let's remember the construction we gave in the previous lecture of associating some random variable, taking rational atom probability to another one that's uniformly distributed. So take this u prime that's uniformly distributed over n, as in a previous construction. In this construction, we have u prime. Let's recall, when you fix the outcome of x to be a, then this random variable is uniformly distributed over v sub a, which is a subset of n, where v sub a, recall, form a partition. It's a partition of n, with v sub a equals to ma. All right, so all we need to know is, look, what have we proved? We prove that what we need to prove is true, dropping conditioning, when the conditioned one is uniformly distributed. When x is uniformly distributed, we can drop it, and we prove it. Now, this is some strange looking guy that's also uniformly distributed over something. We don't care about what this something is. It's uniformly distributed. So that implies that by the special case we proved, we just proved, we have the conditional entropy of y conditioning on this u prime x equal to a. This is a random variable. Is at most, we can drop the conditioning. It's at most hy. Okay? This is true for any choice of a. That means we can also further drop this x equal to a, right? So if you drop it, we have h of y conditioned on u prime. If you drop a, then you just have a random variable x here. It's at most h of y. We are almost done. Now, on the other hand, we have this random variable u prime condition on the choice of x is uniformly distributed over VA, some sets. What that means is that this means that given x equal to a, this u prime now is given this u prime is uniformly distributed over VA. It has nothing to do with y. It's independent of y. How y looks like has nothing to do with how u prime going to be distributed. U prime going to be uniformly distributed. Yes. By independence, then, what this implies is that the conditional entropy of y, conditioning on u prime and conditioning on x equal to a, equals to, since u prime is independent of y, we can drop this guy and equality holds. All right? And this is true also for all a. That means we can further drop this fixing x. This implies that h of y u prime x equals to h of prime y x. So in other words, conditioning on x, u prime and y, they are independent. We are done now. Let's see why we are done. Look, we have these two. So this is at most this guy. That's it. That's the thing we want to prove, right? This is drop-in conditioning. The proof is a little bit, takes a couple of steps, but remembering it's easy. If you forget about what X told you, you can only increase your information you get from Y. So here's the important lemma, sub-additivity. We've seen it before. It says that you have random variables, x1 to xn, any random variables. X1 to xn. Then we have their joint entropy. The joint information you get from them is at most the sum of the information you get from each individual one of them. Okay? You cannot get more than the sum of all stories that they told you, right? Proof. This is basically a couple of 2 lines using the properties that we've proved so far. Now, things become easier now after the theory we built. First, if you look at this random vector, from now on, if you look at the random vector and you have an entropy of it, the first thing should come to our mind is to use chain rule to expand it. So by chain rule, what is chain rule? Let's recall. It says that the entropy of this random vector equals to just in h of x1 plus h of x2 on top of x1 plus h of xn on top of x1 to xn minus 1. All right. Now we can do dropping conditioning. If you drop this conditioning, entropy is gonna only be larger. So this is at most dropping conditioning. H of x1. So drop plus h of x2, the dot, h of xn. That's it. Very simple. Any question? This is subadditivity. Joint information we get is no more than the sum of the information from each individual. The next one, Schur's lemma, you can view it as a generalization of subadditivity. So what is this lemma? Here it is. Schur's lemma. We have a family of subset of n. So you have F, which is a family of subset of n. It could be a some sets could occur multiple times. Doesn't have to be distinct subset of n, such that each coordinate, we think of 1 to n as the coordinates, the direction. Each coordinate is contained in at least k members of k sets in F, k times. Then for a random variable, for any random variable, we have h of x1 dot 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 to xn is at most 1 over k sum of f in F entropy of x sub f. Where? So what is x sub f? X up sub f is basically you have this random vector x1 to xn. You project it down to the coordinates that are containing f. So if f contains element 1, 2, 4, xf is just x1, x2, x4. First of all, let's see why Schur's lemma is a generalization of this subadditivity. Well, if I take f to be singleton 1, 2, to n, these are my elements of f, sets in F. Then every coordinate of n is containing at least one members of F, correct? Then the join information is at most 1 over 1, which is 1, sum over, what is this? Elements in F are just singletons. And what is x sub I? is just xi, the projective one, right? Which is precisely what's up here. So this is a generalization. And when F is the very special case of singletons, remark it here. Taking F to be the set of all singletons, we have K equal to 1 above, and we recover subadditivity. The way we're going to prove it, we're going to prove an equivalent version in the probabilistic form, somewhat cleaner. Instead of saying a deterministic family of subsets, now let's think of sampling uniform random sets from this F. So we think of F, a collection of family. No, we think of a random subset of N now, and then write this in that form. I'll leave it as exercise for you to prove that these two versions are equivalent. It's not hard. Sherrod's lemma. Probabilistic version. Let F be a random subsets of N, such that, okay, before, when we have a family of sets, we want each coordinate to be contained at least k times. Now for a random set, we want each coordinate to be contained in this random set with decent probability. A lower bound on the probability, such that for any I in N, the probability that this random direction coordinate is containing, this direction is contained in the random set F is at least mu. Probability mu. Then for any random variable x1 to xn, we have, in the probabilistic version, it says the entropy of x1 dot 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 to xn is at most 1 over mu expectation over f entropy of the random projection of x to the random set F. Let's prove this. Okay. That's so F is a subset of N. We can then order, let's order the elements in F. So let's I1, I2, order them. This is elements in N, right? IK be the random elements in F, in this random set F. Again, as I mentioned, whenever you see this joint entropy, entropy of a vector, let's use chain rule to expand it. Chain rule says h of x1, xn equals to, sorry, I'm going to do, I'm going to use chain rule to expand this guy first. Chain rule expanding XF. XF, remember, what is this guy? This is X. It's a random vector Xi where I lies in F, right? So we know the I in F are these elements. So by chain rule, expand it out, equals to, let's first write it. This is elements of F. So it's this guy, this just by definition of this IK, equals to H of Xi1 plus H of Xi2 given Xi1 plus dot 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 plus H Xik given Xi1 dot 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 Xik minus 1. Chain. Now we're gonna do, instead of dropping conditioning, we're gonna add add more conditioning. This will decrease the entropy, right, in the opposite direction. If you drop the conditioning, you're going to increase the entropy information. If you add conditioning, you're going to decrease it. So let's add more. How are we going to add more? Well, here, before we conditional x I1, and remember I1 is less than I2. So we can stick in all x1 dot 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 to xi2 minus 1. We condition on more, the initial segments before I2. So conditioning more. For shorthand notation, let's write hxi, h less than I, to be the conditioning entropy of xi, condition on everything before xi. All right. So in this way, we have this guy. Oh, sorry, it's at least. Conditioning more is going to only decrease the information. So it's at least I in F, h of xi, h of x less than I, right? That's the adding conditioning more. This by dropping condition. Okay. This is true for any outcome of F. So we have, you can now take the expectation. If it's always true, it's also true taking expectation. So we have the expected entropy of XF is at least expected expectation of this guy. Okay, let's write what this is. Look at here. We sum over all elements in F, I, and then we take the expectation F. This is the same as you sum over all elements in the whole set of directions, the probability that I is in F times h of xi, h is less than xi, right? Let me highlight this guy, is the same as this guy, which is at least by our assumption, every element is covered in terms of probability is at least mu for all such I. So this is at least mu times sum over I in n, h of xi, h less than xi. Lo and behold, what's this guy? This guy by chain rule is precisely the joint entropy of x1 to xn. We are done. You just move inequalities around. This guy is at most 1 over mu of the left-hand side, which is the inequality we want to prove. Any questions about proof? It takes less than a page to write it. So let's summarize it. Schur's lemma in this probabilistic form. You have a random set of coordinates such that each direction is included with probability at least mu. Then the joint entropy is at most 1 over this lower bound on the atom probability 1 over mu times the expected entropy of the projection to the random set F. The proof is basically, well, just by chain rule. That's it. By chain rule, we expand this random projection, dropping conditioning, and it just pop out. Okay. Now let's see some application of Schur's lemma. If there's no question, let me see. Okay, good. There's no question. Application. The application is the famous inequality, the Loomis-Whitney inequality. It's an inequality that estimates the volume of an n-dimensional body in terms of its projection. This is estimates this inequality estimates the volume of an n-dimensional body in terms of its projections. In particular, in terms of its n-1 dimension projection. So let's define something. Let's look at the for a measurable set K in Rn, let's write volume of K for its volume. Okay, just a notation. Now we say for I in n, let's define the projection pi I pi I is the projection to the n-1 dimension, one dimension lower, to the hyperplane xi equals to 0. Okay. In other words, pi I of x1 dot 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 to xn is just x1 dot 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 to xi minus 1. Now xi, the i's projection disappear after projection. I plus 1 dot 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 xn. Here's a picture. If we have n equal to 3, right, and I equal to 3 also, x1, x2, x3, 3 direction, right? Oh, maybe I shouldn't say x1, x2, x3. It should just say this direction 1, direction 2, direction 3. Now you have some sets y here. Which is, let's say x equals to x1, x2, x3. You get projected down to after pi 3. Which is just x1 and x2. Okay. Projected down here. Now we can state Loomis Whitney inequality. As I said, we have a measurable body K in Rn. Then we have the volume of K is at most the product over the projection onto each hyperplane, the volume of them. Pi I. This pi looks like product, right? I should write it smaller. Pi I, the projection of K, but I need to raise to the power 1 over n minus 1. Okay, let's try to first see this inequality is not insane. Sanity check. Why this makes sense. It is optimal in particular when K is axis-aligned boxes. Remark. Height for K being axis-aligned parallel boxes. Here's example. If K looks like this, right? 3-dimensional box. Okay, and with A, B, C are the side length, then what's the volume? Volume of K is ABC, the product of 3 lengths. The volume of pi 1 of K is what? Pi 1 of K is x1 equal to 0. So it's here. This is pi 1 of k, right? Which is A times C, okay? Pi 2 of k, you can check, is B times C most likely. And pi 3 of k is A times B. So multiply them all together, you get square of this guy. But remember, we have 1 over 2, 3 minus 1. We are in 3 dimension. Here, n equals to 3. We are in R3. Okay, let's see the proof of this. The proof of this is we'll first use this discretization. K could be like the smooth shape, right? But we can use a limiting argument to assume that we can use cubes of the same size to approximate, for any like this smooth body, we can use cube to approximate its volume. And when you take the cube smaller and smaller, this error at the boundary is gonna be the smaller and smaller. So you can arbitrarily well approximate it using cubes of the same size. And you can, using smaller and smaller cubes, you can use scaling and then use limiting to approximate arbitrarily well. With that being said, we may assume using standard scaling limiting argument, we may assume that K, the body we consider, is the union of unit boxes that are axis aligned. Union of axis aligned unit boxes. Unit boxes means the volume of each box is 1. So the volume of K is precisely the number of boxes now we have. We make this problem discretization. So the volume of K is precisely the number of unit boxes in K. Furthermore, we're going to identify for each box or cube, we identify it with its center. Each box has a center, and this is 1-to-1 bijection. In other words, you have your box. This is a unit box. You look at its center here. Okay. We think of the blue box, unit box, as the red center. They are the same. 1-to-1 correspondence. Then, okay, so what do we want to do? Let's see. We want to get the upper bound on the volume of K. In other words, we want to get the upper bound on the number of unit boxes in K. Remember, how are we going to estimate the cardinality of the discrete set? Now it's a discrete set, a set of boxes. We associate it with entropy. If we uniformly random sample a box in K, the entropy of this random box will be the same as log of the volume, log of the number of unit boxes. That's how we associate it. So basically, we're going to randomly sample a box from K and give an upper bound on its entropy. And the upper bound will be, the entropy will be log base 2 of this guy. If you can prove that, we are done. So we're gonna as I said, we're going to take X, which is a uniform random box in K. Uniformly random sample over boxes in K. By maximality, we know that entropy of this random box equals to log of the volume of K, right? So our goal now becomes we need to prove this guy, take the log, need to put entropy is at most log of the right-hand side. So need to show entropy of X is at most log of the other side is what? Is 1 over n minus 1. Sum, product becomes sum after taking log. And then log of volume of the projection of K. This is what we need to prove. The new goal now. Okay, compare this and this. Any question? Good. So this is our new goal. To prove this, we'll first notice that we want to write X in terms of a vector form, and then use chain rule, Schur's lemma, whatever. How do you write it in the vector form? As we said, we're going to identify each box by its center. So this center now is a point in Rn, which in particular has n coordinates. So we can identify, we think of X as the center. Identify Y with the center of this random box in K. We can write then X as x1 to xn, where xi is the coordinate of the center. Xi's are coordinates of okay. We're going to use Schur's lemma. So for Schur's lemma, we need to define the random sets. Okay. This random set will be a very natural one we should think of. We have n different projections to n different codimensional one hyperplane. The most natural one will be we uniformly random choose a projection over all these n directions, resulting in n different projections. And the random set will be the coordinates we projected to. So let pi be a random projection, uniformly random sample over pi 1 to pi n, projection to the codimensional hyperplane. And let C be the random set, which is subset of n, be the random set recording the set of coordinates that pi projects to. In other words, so if pi equals to pi I, then C is just nothing but n with I removed, right? In this notation, And then for a vector, let's say z equal to z1 dot 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 to zn, a point, we're going to write pi z in this notation. Pi z is what? It's a random projection of z onto this random set random set c, right? So it's basically z sub c. We're going to write this, where z sub c, oops, is zi, I in c, random projection. Now, since we need to, C is the random set we're going to apply in Scherer's lemma, we need to estimate the probability that each direction appears in I. What's the probability? Get the lower bound on this probability. So since as pi is uniformly distributed over all direction of projection, we have that, in other words, C is a random set that looks like this for all I equally likely. So any direction I is included in C with probability n minus 1 over n, right? A random, uniform random n minus 1 sets is included in n, in C. So the probability that I in C is n minus 1 over n. Let's call this guy mu. That's the mu we're going to apply in Scherer's lemma. Now we can use Scherer's lemma. We have, this is the guy we want to estimate. Remember, hx1 to xn is at most reciprocal of the atom probability mu. So it's n over n minus 1 times the expectation of the random set C, h of the random projective vector xc. That's Scherer's lemma. All right. This is exactly the same as, by our notation, random projection C is induced by the random set is induced by the random projection pi, right? So it's the same as h pi of x. These two are the same thing. Pi of x is xc. That's how we write it. Okay, but what is this guy? We know exactly how it looks like, because pi is uniform and random, chosen from pi 1 to pi n. So the expectation here equals to n over n minus 1. Expectation is sum over I from 1 to n, 1 over n, pi I of x. Correct? This is the expectation. Okay. Now, n get canceled out. We have 1 over n minus 1 in the front. It's starting to look like the thing we want to prove. 1 over n minus 1. Sum over I from 1 to n, h of pi I x. But what is pi I x? Well, at the end, note that pi I x takes values in pi I of k, right? X is a uniform random box in k, and I is the projection to the ith direction. Pi I x is, it takes some value over the projected body pi I k. Trivial. Then by maximality, we know that the entropy of this random variable, since it takes value in this set, is no more than log base 2 of the volume of this projection. Okay. Plug it up there, we are done. So implies, let's write down this guy. H of x is the most 1 over n sum I from 1 to n log volume of pi I k. This is precisely what we need to prove. We are done. Any question? Oh, we're right on time. Okay. So that is what we want to cover today. Schur's lemma, the most important one, and the application of it to prove this Loomis-Whitney inequality. Any question? So let's summarize it. Today, we talk about dependence. Dependence says if a random variable is determined by another, then it does not offer more information than the other. So dependence property. Okay. And then we talk about if you take at least 2 values, then you must be positive. So if the random variable is not certainty, it implies entropy positive. And then we proved that the chain rule and then drop-in conditioning can only increase the entropy information. Using drop-in conditioning, we can then prove subadditivity. Subadditivity, it's a special case of Schur's lemma. Then an application to Loomis-Whitney inequality. Okay, this is today's material. If there's no question, I will see you guys again next week on next Tuesday. Right.